Hey everyone, welcome back to Cracking the GRE Math Subject Test. This is Calculus 2 and we're on question number 26. In this question we're asked to evaluate this integral along the path C, which is defined by this equation from 1, 0 to 0, 1. And they're telling us that this equation can be parameterized as such: x equals cosine cubed t, y equals sine cubed t, as t increases from 0 to pi over 2, and that seems like a hint, but actually if you try to plug in this parameterization into the integral, you're going to end up with a big mess. And so this question is kind of tricky because what you have to realize is that this integral is equivalent to, well, it's like the integral of a vector field. It's a line integral of a vector field, if f is a vector field. And what you have to do, where this is the first element of a vector field, and this is the second element of a vector field. And what you can do here is, or what you need to do here is to realize that this vector field is actually a gradient field, and then use the potential field to evaluate the integral. And so I'll show you what I mean. First of all, what is a gradient field? How do you know if f is a gradient field? Remember that if you call this, let's see, if our integral is, let's say, m, some function m of xy plus, n dy, and this is our m and this is our n, then if the derivative of m with respect to y is equal to the derivative of m with respect to x, then f is a gradient field, which is great because then that means that the integral is path independent, and we can just use the potential field evaluating it at the endpoints. So let's see, what is the derivative of m with respect to y? That's going to be, let's see, we have to use the product rule, so derivative of y is 1 times cosine xy plus y times the derivative of cosine xy with respect to y. That's going to be negative x sine xy, and minus 1 is going to drop out. And what's the derivative of n with respect to x? That's going to be, 1 is going to drop out, and we get derivative of x, which is 1 times the derivative times cosine of xy plus x times the derivative of cosine xy with respect to x, which is going to be negative y sine xy. So these two are definitely equal to each other, which means that f is a gradient field, which means that we can find a potential field. So what we want to do is to find little f such that the gradient of that little f is equal to big F. So what does that mean? It means that if we take the integral of this m, y cosine xy minus 1 with respect to x, let's see, well, what's that going to be? It's going to be y divided by y is 1, so it's just going to be cosine xy minus x plus some function, it's a little g of y. And if we do the same thing for our function n, that's going to be 1 plus x cosine xy dy. We're going to get y plus, again here, the x is going to cancel out, and we get cosine xy plus some function of x plus some h of x. So we can see that the cosine of xy appears in both of these. So our function, our potential function f, is going to be cosine xy minus x plus y. And now our integral, which we can write as f dot dr along c, because f is a gradient field, it has to be path independent, which means we can just look at the value of the potential function at the endpoints. So this is going to be f evaluated from 1, 0 to 0, 1, which is going to be, if we plug in, oh sorry, this is supposed to be sine. So, sine xy, same thing here. So this is going to be, let's see, if we plug in 0, 1, we get y is fix this as well, sine of xy. Okay, good. So now if we plug in 0, 1, we get sine of 0, which is 0, minus 0 plus 1, minus sine of 0, which is 0, minus 1 plus 0. So altogether, this gives us 2, which is answer E.